So as Maria said, I'm going to be giving some examples of data-driven discovery of materials for photocatalysis and power electronics. And if you're interested in our group's research, please visit our group website. We have a data website as well and a GitHub page where we curate our codes. So the first topic I will touch upon is that of discovery of photocatalysts. And I'm going to start by presenting one success story which we had in the recent past. But predominantly, my group has been focused on discovering photocatalysts for water splitting, which you see here on the left, and CO2 reduction. And the challenges with both these processes are that even though we can use sunlight to generate renewable source of energy, such as hydrogen gas for water splitting and various fuels for CO2 reduction, the challenge is that the existing photocatalysts may or may not are not very efficient, and they're competing reaction products. There are multiple properties which each photocatalyst needs to satisfy, and some of them are intrinsic properties of these materials. Here I list some of the research we have done in the discovery of photocatalysts in these two areas. And the most interesting one to me, and I think this audience would be this specific example shown on the right-hand side, where we did a computational and experimental search. And this was very much enabled by one of the national data infrastructures, that of the materials project. So we searched for photocatalysts based on some of the intrinsic properties which are available in the materials project. And these are shown by these orange screening tiers. And then our experimental colleagues at Caltech were able to synthesize them and determine their activity using high throughput experimentation. I want to draw your attention to this specific last stage of the computations, where we determined the aqueous stability, and we found 27 manganese oxides out of 66,000 materials in the materials project database, of which our experimentalists were able to grow nearly 50% of them. So it shows that the power of all of the data available in the materials project in identifying potential candidates is quite high. And then at the end of the project, we identified 5 new photocatalysts which had never been used for water splitting, and we demonstrated their photocatalytic activity. So this aqueous stability, indeed, in the materials project at that time, we did not have the ability to generate so-called electrochemical stability maps. Traditionally, if you want to determine the aqueous stability, which is very much a part of photocatalysis, especially in water splitting, because it happens in aqueous media and it happens in oxidizing conditions. In CO2 reduction, it is predominantly done in aqueous media, but in reducing conditions. So traditionally, we either use quantum mechanical methods or explicit or implicit solvation models to investigate the physics and the chemistry in the presence of electrochemical media. At the time, there weren't any generalized theories to look at the electrochemical stability of materials from first principles, but using the existing data in the materials project, we devised a technique to compute electrochemical stability maps, which show the stability of materials as a function of potential and pH, demonstrating what a material would perhaps passivate into, or perhaps it would corrode or just be stable. And we established a numerical scale of stability. We made this formalism available on the materials project website. So now when you go on the materials project website, you can just, by a click of a button, get these maps for all the materials in the materials, 130,000 materials in the materials project. It's also available on the GitHub page. So such functionalities are really important to integrate and make available through national data sites. And this has really transformed the way we assess the electrochemical stability of materials for many applications. For example, these ESMs are widely adopted for identifying battery cathodes, chemical sensors, coatings, and also developing recursion theories. Here are some of the examples I show on the right-hand side. And we recently wrote a review article highlighting this method and how it has made transformative changes, especially in the field of photocatalysis. So what do we need next? Determining the aqueous stability was very important in photocatalysis. But what's next is really going from materials genome to surface genome. The existing materials databases do a great job on curating the properties of bulk materials, especially DFT computed properties, and there are several well-known materials databases, including experimental databases like the ICSD. The next steps, in my opinion, which would really benefit this field would be to look at the surface properties, the properties of adsorbents on these surfaces, look at heterostructures. And these are the key reaction areas or key physics and chemistry areas in the applications of catalysis, as well as batteries and even nanoelectronics. We should, as a community, be looking at systematically curating the structure and properties of surfaces and interfaces. And there are several efforts across the country, but they're isolated, and perhaps a systematic integrated approach would benefit the whole community at large. So that was about photocatalysis, and I want to briefly touch upon power electronics as well. I'm a trust lead of one of the EFRCs funded by DOE, the Ultra Center, and there we focus on power electronics. One of the goals as a part of the center is to discover materials for power electronics and understand defects and heterostructures of materials for power electronics. For power electronics, we are mostly looking at wide bandgap or ultra-wide bandgap materials. These materials have band gaps larger than 3.5 eV up to 10 eV. So these are very large gaps. There are very few wide bandgap or ultra-wide bandgap materials that have been developed to date. These are some nitrides, diamond, and gallium oxide. We could expand this phase space and bring in more materials into consideration using computations. And here I show some of the properties which can be determined using computations, and except the structure, you'll notice all the ones listed in red, such as band gaps, band offsets, impact ionization rates. These are all very much dependent on the electronic structure. And I think in this audience, majority of us are aware that for large gap materials, traditional DFT under the LD or the GG approximation severely underestimates these properties. We need something like mini-model perturbation theory to be able to study materials for power electronics and discover and design them. As a part of the center, we have developed a high throughput workflow package called PyGWBSE. And the code is available on GitHub. It follows standard practices as those used by the materials project team. This code makes the very challenging task of converging the interrelated convergence parameters and optimizing the computing time, which is very high in these many-body perturbation theory calculations, and then automatically curating the data as well. This code, we recently published the article for this, and using this code, we have been curating the data in the UltraCenter database. This data is available through an API, as well as our data website. And right now we have about 1,000 or so GW computed properties of materials. And I want to mention this is one of the largest. We also have excitonic properties of about 500 materials, and that's the largest database of excitonic properties. The database also has some data from experimentation done as a part of the center. And specifically in this field, the challenge is that existing national data bases mostly focus on DFT. We need more effort in developing workflow packages as well as data curation schemes for domain-specific simulations for power electronics or microelectronics, which require many-body perturbation theory, for instance, to study heterostructures, the various point defect energies, which affect the device performance.